Okay, so we've got a video here on particle interactions, aka simple diagrams to represent these reactions. They're not technically Feynman diagrams because Feynman diagrams are a bit more complicated than these ones, and as a result, there's quite a lot of confusion if you try and Google these diagrams, because actually in Feynman diagrams, traditionally antiparticles are represented with the arrows going the other way, because the arrows represent the kind of like flow of matter, and antimatter goes the other way. So but these are the ones I've been through the past paper questions and everything, and these are the ones that AQA talk about. I mean, the first thing in the course of an AQA used, so these are fine. I think they're just not perfect Feynman diagrams, but it is what it is. These are diagrams. There's the 4 diagrams you need to know to represent 4 things quoted on the specification: beta minus, beta plus, electron capture, and electron-proton collisions, with the weak boson as the exchange particles. Now, first of all, there's 4 fundamental forces. The strong nuclear force, and the exchange particle of that is the gluon. The electromagnetic force, the exchange particle of that is the virtual photon. The weak nuclear force, which is responsible for all these kind of decays and interactions that you study, and the exchange particle is either W plus, W minus, or Z naught bosons. And then the gravitational force and the exchange particle is the graviton. The ones in brackets you don't actually have to know, but they do put them sometimes on the exam. You only have to be able to recall that the exchange particle for the electromagnetic force is the virtual photon, and the exchange particle that governs the weak nuclear force, kind of like conserves charge within weak nuclear decays, is W plus and W minus. And you need to obviously know what the 4 fundamental forces are. This is like a bit of like very heavily advancing physics, but it's just what's on the spec and what you have to know to a certain extent. But it is very interesting. The gauge bosons or exchange particles and are interesting with how they kind of explain how forces can act at a distance. So this is an example of 2 electromagnetic things, right? So this is a positive person and a negative person. Now, this positive person, this negative person, these 2 positive people, they do not like each other. They repel because they're positive. And the idea is that without actually touching each other, they could exchange something, say like a basketball or a bowling ball or something. This person could throw a bowling ball at this person, and actually they would both move apart because of momentum. If this person was stationary and the momentum suddenly fired out a ball in that direction, this person would move this way. And surely when this bowling ball or basketball, or however violent you want to be, hits this person, they're going to move backwards. So by kind of transferring this particle over, they've managed to move apart. And this is the model for how these particles, exchange particles, can mean that, there can be a gravitational force between you and the sun without actually you having to touch the sun, and it's through an exchange of one of these particles. Now, the model for coming closer together using an exchange particle is slightly more tricky. You have to imagine that this person, in fact, flings out a boomerang. This is supposed to be a boomerang this way, and by flinging out a boomerang in this direction, conservation of momentum means this person's going to move in this direction, and the boomerang travels around, hits this person in the back, and then when it hits them in the back, they surely move forward. So exchanging these particles can model how we can have forces happening at a distance, right? How things can interact each other at a distance, and it's by exchanging a particle called an exchange particle. Now, the weak nuclear force is responsible for the decay of particles involving leptons, and it is governed with the W plus and the W minus boson. Now, there are 4 diagrams that you need to know about, right? There's beta minus decay. So beta minus decay is when a neutron decays into a proton plus an electron plus an electron antineutrino. We know about this one because there was a kind of like this one, the electron was produced with a range of kinetic energies, implying conservation of energy was violated. So no, another particle must be produced, must be an anti-electron neutrino because of conservation of lepton number within this reaction. Now, actually, a neutron is actually up, down quark, and a proton is up, down quark. So actually what's happening is a down quark is turning into an up quark. Now, at the kind of rules for these simple diagrams are that we start at the bottom and we work our way up, right? So you start down here at the bottom of the diagram and you work your way up. So we started off with the neutron, which is fine. That's not what we know. Now, at every single point, every kind of vertice or intersection here, wherever the lines branching off, you conserve charge. So effectively, we had 0 charge here from the neutron, and then the proton becomes +1 charge. The W minus boson in this direction becomes -1. So we've got kind of 0 equals +1 -1, which is fine. Or if we think of it in terms of quarks, we've got -1/3 quark becoming +2/3 -1. Well, that all still works out because -1/3 is equal to +2/3 -1. So we're conserving charge at each vertice. You can't like violate conservation of charge. So that means this must be a W minus boson going in this direction, just to conserve charge at this intersection. The W minus boson then, again, we conserve charge because we've got -1 here and we have our electron, or sometimes our beta minus. It's the same, interchangeable, they mean the same thing. And then this is neutral, right? So they kind of peel off like this. These arrows, this like, it doesn't represent like physically positions of what happening. It's just showing the flow of matter and where the matter is going. So, you know, it's not actually like physically what's happening. It may be that the proton and the neutron remain stable, but the arrows are showing the flow of where the matter is going. So beta plus decay is sort of like opposite of beta minus decay, I guess, but this time you start with a proton, and the proton turns into a decays into a neutron plus a positron plus an electron neutrino. So this then, therefore, a proton is actually up, up, down, and it's up, down, down. So it's actually technically an up turning into a down. So they could show you either ones on these. At this vertice, charge must be conserved, so it's positive here. That's neutral because it's a neutron, so 0 charge, so this must be positive along here. And then at this vertice, we must have positive coming out, neutral coming out. And it can be either the symbol for the positron, which is the antiparticle of an electron, or this beta plus. The next one is electron capture. Now, electron capture is sort of like undoing of beta minus decay. And so this time we have kind of like 2 starting at the bottom, because we start off with an electron and a proton at the bottom here. And then they exchange a W plus boson. Now, if it's the other way around, then it becomes an electron-proton collision. But this one here, it's the proton kind of like is the one that we're following through. So the positive charge goes this way, it meets a negative charge there, and it produces a neutral particle. And so you start off within this one with an electron and a proton, and you end up with a neutron and your electron neutrino. And obviously, of course, it could be the up and then the down. So it's kind of like undoing beta minus decay, if you like, but it's its own interaction. It's called electron capture. You need to know this diagram. These are the diagrams they show in the exams, so you need to recognize this simple diagram to represent this electron capture. Now, electron-proton collision is slightly different because it is an electron colliding with a proton. So we kind of start, if you like, with the electron, W minus boson, and then the proton collides with the proton, and then you end up with your electron neutrino and your neutron. They're very similar diagrams. The only difference is the boson and the direction that it goes. And actually, in one of the exam questions, when they were asking you, they were actually accepted either way, whichever one you drew. It's kind of like whether it's electron capture or whether the electron and proton are colliding, exchanging the W minus, and then becoming the electron neutrino and the neutron is pretty negligible, you know. And so in the past, when they've had exams on this, they don't get too hung up on it, is what I'm trying to say. Now, so sometimes though, they show you these other diagrams. This was an example of a diagram they could show you where they say, okay, well, this is something else that's happening, not something you have learned, because you will learn all these 4 diagrams and how to draw them and the differences between them. So you can, more importantly, rather than draw them, they ask you often to identify them, which is the correct diagram for electron capture, which is the correct diagram for beta plus decay. But in these ones, we've not known this before. So this is a proton colliding with an electron antineutrino. We know that they're kind of both existing at the same time in time here, and then they become a positron here and an unknown particle, and we've got to figure out what the exchange particle is. It involves leptons, so it's going to be the weak nuclear interaction, and so we're just going to think about how the charge is conserved to figure out what it is. I mean, the only ones I need to be able to recall are W plus and W minus, so it's kind of got to be one of those. But this is a neutral particle because it's an antineutrino. Here we go this way, we've got a positive. So going here, we must have a W minus. Yeah, because the zero charge becomes a plus 1 minus 1. So 0 is equal to plus 1 minus 1. At that vertice, charge is conserved. Then, carrying it on, here, entering this vertice, we've got a minus 1 here, and then here it's a plus 1, and then what's it going to be? Well, this particle has to be a neutral particle. We also know, because of conservation of baryon number, that it must be a baryon, and the only neutral baryon that we're expected to know about is the neutron. I mean, I guess you could put other neutral baryons, and they'd have to allow that as well, but the only neutral baryon that you know about is the neutron, so it must be a neutron coming out there. So I hope that helps. Just give me a comment if you want me to go through anything else in more detail, or you think there's a better way that I could do this for you. Thank you.